Okay, so the last couple of videos were a little bit heavy on concepts and definitions. So we move on and shift gears a little bit toward some more practical skills. So this section will be about exploratory graphics, visualization of raw data, data checking, and error corrections. So after you have successfully put your experiments out and recorded your data, that would be the first step, to look at your data, to check that everything has been entered correctly. And you should actually have the skills now to do error corrections in R. If you find you have to do this, you can go back to the data management lab to actually not correct these things in Excel. So leave your data entry sheets intact. It's always good to keep the original. But if you think you have an outlier, then you can correct those in R. So you can either selectively remove those values based on particular thresholds. And the nice thing is, if you do that in code, you can change your mind later. You just change one value in your code and you try an error correction with a different threshold perhaps. Okay, so the graphs that we will cover in the next lab are scatter plots, histograms, and box plots. And you're probably familiar with scatter plots. These are simply XY relationships that you can see. Histograms give you the distributions of any single variable. So for each of these axes, I could look at a distribution of those values. And the box plots are actually sort of a scatter plot on the side and a little bit more compact. So if you look at this one here, that basically gives me the range, just like the histogram, and it gives me the central 50% of the observations and the median, which is the big bar here in the middle. So usually you display them like this, so 90 degrees turned to the left. And it's as close as looking at a table in detail as you can get. So scatter plots actually show you every single point. Histograms combine those points in classes so you can see the distributions, and box plots essentially do the same thing, except in a slightly more compact way. Now, the reason why you want to do this is if you have outliers, they will pop out, or if you have errors, they will pop out in these types of graphs. So before you do any statistical analysis, before you calculate summary statistics, those are the tools for error checking and correction. A very nice way to make this point that this is actually really necessary is Anscombe's quartet. These are sets of X and Y data, so just a table with X and Y values, and they look very different, right? So you have this correlation here, and you have this curve, you have a very tight correlation with an outlier here, and then you have this vertical row with an outlier. And the amazing thing is that all these variables or point clouds have the exact same summary statistics. So the mean of X is 9 in all 4 cases. The mean of Y is 7.5 in all these cases. The variance or the standard deviation is the same, so 11 and 4.1. The correlation coefficient, if you calculate correlation coefficients for this, they're all the same, 0.816. And you can calculate a linear regression equation. It all looks the same. So if you were to summarize this data with a bar chart, for example, they would all have the same mean, the same standard deviation, so you would see no difference. You would have no chance to find those errors or outliers, or visualize that they have these types of correlations. So while summary statistics can be fooled, the graphs here that we cover in this lab cannot be fooled. So they would all look different for those different data sets. So scatter plots would look different. We've seen that already. Histograms would look different, and the box plots would all look different. They would show you the outliers. Those are much better tools for error checking, or even for understanding what's in your data, than just proceeding straight away with descriptive statistics and summary statistics. Okay, a little bit more detail on the 3 graph types that may come in handy. Scatter plots are pretty common. I'm sure you're familiar with this. The one thing you might want to keep in mind is that the X and the y-axis are reserved for independent variables. So x always has to be the independent variable and y always has to be the dependent variable. And that's also just a convention. If it comes to just graphical representation, there's really no reason why it should be one way or the other. But you confuse the hell out of people if you put, let's say, yield of some agricultural crop and climate over here on the y side, because that would imply that the yield influences the climate. So make sure that you don't confuse these two. And if you implement this in R, the order here, this can be written two ways. You can either say x comma y for the plot command, or y with this little tilde sign here as a function of x that reverses the order. And it's similar to math notation where you simply say y is f of x, right? Function of x. So ax plus b as a simple linear regression example. So it's the same idea. This tilde just means as a function of. So next are the histograms, and you probably also know what that is. But just to be sure, I want to go over this quickly, how they are constructed. So you can think of this is really a single axis or a number line. And if you were to order your observations on that line, on that x-axis line, starting with the smallest one an 8 and the biggest one a 47, you could also bin these observations. So in that first bin from 5 to 10, we have that 1, 8, and that represents one observation here. And then in the next bins and so forth, we have different numbers. So sometimes these numbers are actually put on top of the bars. So those are the frequencies. And you can tell that this is a histogram and not a bar chart, because usually those are all, there are no gaps between those individual bars. And so in bar charts, gaps are the default. So you can have groups as well if you have like a factorial design with different treatment levels. We'll get to this a little later. But generally, if you have a gap here, that means there's nothing in that particular class. So usually you shouldn't have an issue distinguishing between what those two graph types are. And obviously the y-axis here is a frequency, and that is your x. And in case of the bar chart, that is actually your single axis, and your x-axis in quotation marks, those are the classes. And the third widely used diagnostic plot is the box plot. This is a similar idea to the histogram. So again, if we can think of our single axis that represents a single axis, we will have the range of observation indicated by these whiskers, and then each of those sections here is a quarter or a quartile. And so a quarter of my observations falls between this whisker and the main box. Then the second quartile goes to the median. The third quarter of my observation goes to the 75th percentile, and the fourth quartile goes to the full range. Now I should warn you that these quartiles, they are not consistently referred to. It depends a bit on the context. Oftentimes you say, oh, I'm in the first quartile of the class, or I'm in the top percentile. That doesn't necessarily mean the first down here, so it depends on what kind of scores you have. If you have the North American grading system, this would be referred to as the top quartile or the top percentile. So another interesting thing about box plots is that they identify outliers, and this has been also a convention where, in fact, an early statistician called Tukey, we'll hear from him later again, just came up with an arbitrary or subjective sense of what an outlier represents. So if you measure the distance from here to here in actual numbers on your x-axis, that's also called the interquartile range. And if you start from the top of your box and measure the distance that's 1.5 times the interquartile range, that represents your inner fence. So everything between the inner fence and the outer fence would be considered a near outlier. And then the 3 times the interquartile range determines the outer fence, and anything out there, that's called a far outlier. So box plots can help you determine what's an outlier or not, but But keep in mind that this is just an arbitrary threshold that can guide you. It's been made with good judgment, but there's nothing magical about these numbers. Another thing that you can assess very easily with box plots is the kurtosis or skew. Kurtosis simply means whether your distribution is fatter or narrower than a normal distribution. A normal distribution in the kurtosis metric is defined as 3. If you get a number that's smaller 3, it's a fatter, and a larger 3 would indicate a narrow distribution. And for skew, it's a similar thing. So those metrics are positive or negative. Usually you have positively skewed observations. So if they are bigger, they're really bigger. If I were to draw a distribution here, it would start steep and then have a long tail out here. So you have the far outliers toward the high value. So that would be a positive skew. If you do have it the other way around, it would be a negative skew. But those are generally not very common. That's the lab 3 now that you can do, so that you have these analytical graphical tools at your disposal when it comes to checking your first raw data that comes back from an experiment or from a field campaign.